Here we are on page 4. We are going to look for functional groups, very specific atom arrangements. I'm going to start over here. We have a carbonyl. I'll probably just do all the carbonyls together so you can see how different they are. You can see this first one has a carbon on one side, and key part is that it has a hydrogen on the other. So this is an aldehyde. Aldehyde, and spelling does make a difference. We then have over here another carbonyl, carbon-oxygen double bond. We see on one side we have a carbon, and on the other side we have an oxygen. That oxygen is connected to another carbon, which makes that functional group an ester. Ester. Third carbonyl, we have carbon on one side, carbon on the other. Some people say this looks like a key. This is a ketone. There is no Y in ketone. If you put a Y in there, I'm sorry, but you did not get that point because spelling matters. Next, we have another carbonyl. This carbonyl has a nitrogen on one side, which means it must be an amide. Amide, as long as the D is very obvious. We then have our final carbonyl in the compound. The carbonyl on one side has a carbon, on the other side is an oxygen connected to a hydrogen, so this is a carboxylic acid group. Those are all the carbonyl derivatives. Let's look at other stuff. Let's take a look at this SH group. When we have a carbon connected to a sulfur connected to a hydrogen, we call this a thiol. Other heteroatoms being nitrogen. That's just the fact that it's a nitrogen by itself that's not involved in a double bond. It's not next door to a carbonyl. This is an amine. We then have an oxygen with carbons on either side of it. There are no carbonyls in here or double bonds. This is an ether group, carbons on either side of oxygen. And then we have the the hydrocarbon groups. When we have a carbon-carbon double bond, this is called an alkene, 2 E's. Carbon-carbon triple bond is when we have an alkyne. So one letter makes a really big difference in functional group identification. The next part is nomenclature. You're going to draw skeletal structures for any 3. I'll go ahead and do all 4. We start by doing the parent name, hexane. 1, 2, 3, 4, 5, 6. Numbering it is always cool. We have an ethyl group on 4. An ethyl group is 2 carbons, and 2 methyl groups on carbon 2. We then have this next one, its parent is cycloheptane. So we can draw cycloheptane as follows. It starts out as a cyclohexane on top, and then it looks like a little bit of cyclooctane, like a stop sign on the bottom. So this is a 7-membered ring. We have a 1-3 relationship between the substituents, and they're also going to be cis to each other. I'm going to move this down a little bit so I have more space to draw that cyclopentyl group. We move up here. 1, 2, 3, 4, 5 cyclopentyl, and I'll go ahead and make this a wedge, and then the bromine over here should be a wedge as well. So you could have done this where they were both dashed. That would have been fine, and so by that I mean if we had the same compound and we put dashes here, that would still be a cis compound. And that's what's going on there. Just as long as there are 3 carbons away from each other, you're fine. Next, fluorocyclopentane is our parent. 1, 2, 3, 4, 5. We have substituents on carbons 1 and 2 that are trans or opposite. We have a tert-butyl group, which is 4 carbons total, but it's a tertiary carbon. Well, it's not really a tertiary carbon in the middle, but the group itself, this carbon has 3 carbons attached away from the, what's it called? Ring. So this is a tert-butyl group as opposed to a regular butyl group. If it had been a 5-membered ring with a regular butyl group, it would look like that. So tert-butyl is an isomer of a butyl group or of butane. And then we're going to go ahead and put this guy wedge because I just chose one. I kind of put it on the wrong carbons. I can fix that by just making this carbon 2 and that carbon 1 because the relative relationship is the same. It's trans, and since the tert-butyl group was wedged, I'm going to make the chlorine group dashed. Now you could have done it where you switched the wedge and the dash. That would have been fine, just as long as the relative relationship between those two groups is the same. And so by that I mean you could get rid of these and switch them out. This could be dashed and that could be wedged. And these groups could be wherever on the ring, up, down, left, right, just as long as they're 2 carbons away from each other. And then last one on this page, we have octane. 1, 2, 3, 4, 5, 6, 7, 8. Never too cool to skip your carbon numbering. On 4, we have an isopropyl group. This is an isomer of a propyl group. So a regular propyl group would have 3 carbons. An isopropyl group is an isomer of that. And we have a methyl group on 3. So those are the solutions to the nomenclature problems. I'll clean these up so you know that these are not actual answers. And I believe that's it. Okay, we'll see you on page 5.